So we're going to find the Maclaurin series here for the function f of x equals e to the negative x. And just remember, the Maclaurin series is a subset of the Taylor series. It's just centered at 0. So the value we use for a is equal to 1. And the Maclaurin series pattern is a little bit easier because we don't have to subtract that a value because minus 0 is different. And then we're evaluating the function and the derivatives at 0. So I'll start off by listing a few derivatives. F prime of x is negative e to the negative x. Taking the derivative of that, f double prime of x, that would be positive e to the negative x. And we already see here that it starts to have a circular pattern. So in this case, we would get negative e to the negative x for our third derivative, and our fourth derivative would be positive e to the negative x. So we can come up with a rule and say that, well, any nth derivative of x, it's just going to be e to the negative x, but it's going to be alternating. So I'll say negative 1 to the n, e to the negative x. And now I'll evaluate all of these derivatives at 0 in my original function. So f of 0 is e to the negative 0, and e to the negative 0 is positive 1. Let's see, we've got f prime of 0. In this case, we get negative 1. Second derivative evaluated at 0, positive 1. Third derivative evaluated at 0, negative 1. Fourth derivative evaluated at 0, positive 1. And we see that pattern here repeating itself. Okay, so it keeps going, repeating itself in this alternating manner. So if we look at our Maclaurin series polynomial expansion, we'll say that e to the negative x, well, that is equal to f of 0, which was positive 1, plus the first derivative evaluated at 0, we got negative 1, so plus negative 1, we're going to have minus 1x. Then we'll get a positive 1, and that is my second derivative, which is positive 1 over 2 factorial x squared, minus, for my third derivative, we're going to get 1 over 6 factorial x cubed. And so if we looked at writing this out, we would get an nth term. We would use negative 1 to the n. We notice we have factorials in the denominator. And that would be times x to the n. So my Maclaurin series polynomial, just going to clean this up a little bit. I've got 1 minus x plus x squared over 2 minus x cubed over 6. And that is equal to the sum, as n goes from 0 to infinity, of negative 1 over n factorial x to the n. Okay, so let's do one more example with a Taylor series. Right? And so the only difference between a Taylor and a Maclaurin series is that the Taylor has just an added detail of we have to subtract that a value from our x's as we work through it. So let's find the Taylor series. And we're going to do this for f of x equals x cubed minus 2x plus 4. And we'll be evaluating this at my a value equal to 2. So we start by listing our derivatives. F prime of x, 3x squared minus 2, second derivative, 6x. Third derivative is 6. So every derivative following this, every nth derivative after this, we're going to get 0, and that would be for any n value greater than or equal to 4, because the derivative of 6 is a constant, and the derivative of a constant is 0. So evaluating each of these at a equals 2, we would say f of 2, my output for that is 8. My derivative evaluated at 2, I get positive 10. Second derivative evaluated at 2 is 12. Third derivative evaluated at 2 is 6. And any other derivative, any nth derivative after 3, 4, 5, 6, 7, I want to write n there. Any nth derivative, if I evaluated it 2, my output's always going to be 0. So my Taylor series expansion here, this original function, is x cubed minus 2x plus 4. And what this is equal to, my first term in the expansion is my function evaluated at 2, which is 8. My second term is the first derivative evaluated at 2, 10, and then we multiply by x minus 2, and that's to a first power, but we don't need to write that. My second term comes from the second derivative evaluated at 2, so I've got plus 12, and then we're going to say x minus 2 squared. And this, of course, needs to be then over 2 factorial. And my third term would be plus 6, and I have x minus 2 cubed over 3 factorial. So now, if I went to go write my next term, I would end up writing plus 0 of anything. There are no other terms in this Taylor series expansion. So I can clean this up just a little bit and at least get those factorials out of this. We'll say this is 8 plus 10x minus 20, 12 over 2 factorial. 2 factorial is 2, 12 over 2 is 6, x minus 2 squared, and 3 factorial is 6, so the 6 over 6 goes to 1, it cancels, and I've got x minus 2 cubed. And I can continue to multiply these out and combine like terms as needed. But I'm not going to deal with all that busy work, because as this is a Taylor series expansion, which is a power series or a polynomial expansion, what I know is, since I started with a polynomial, that if I continued multiplying all of this out, I would end up with the exact same polynomial. So these are going to match exactly, and there's going to be no error here. So doing a, Taylor expansion on a polynomial seems a little redundant, but I think it is a nice way to show you that what you're doing is creating a curve with the least amount of error possible that lines up with your original curve.